Bonjour tout le monde, and welcome to Passmark Chemistry, the channel where we help you to pass your chemistry exams. Well, our next video, Balancing Equations, was requested by one of the subscribers. Shout out to Roya. This is for you and for anyone else who needs help balancing equations. Balancing equations is a subject area that a lot of chemistry students struggle with, including myself when I was first learning this. One of the issues with balancing equations is there's not a lot of theory to it, but there is a lot of practice. The concept is simple enough. Everything in has to equal everything out. But doing that in practice is not always as easy as it looks. This video, I'm going to talk through some of the tips, some of the tricks that I picked up just from doing an awful lot of these. So let's have a look. If I have a reaction like this, methane reacting with oxygen, a combustion reaction. And if we've been studying chemistry, we know that if you burn a hydrocarbon in a plentiful supply of oxygen, you'll get your two products. Your complete combustion gives carbon dioxide and water. So we have the full reaction here, and all the formulas are correct. H2O is water, is always H2O. Carbon dioxide, CO2, O2 for oxygen, CH4 for methane. These are the chemical formulas and they cannot change. I can't change any of the small numbers. The little numbers are fixed in. So this has to balance because we've got an issue here. I've got one carbon going in and one carbon going out. That's not an issue. But four hydrogens going in and only two coming out. I've got two oxygens going in and three, one, two, three coming out. And that's the issue. Everything in has to equal everything going out. This is the concept of the conservation of mass. So I don't change the formulas. I can't change water. If water becomes H2O3, for instance, well, it's something else. It's not water anymore. The formula is fixed. But what I can do is change the amount that I put in or out. So for a chemical reaction, I think of it a bit like a recipe. If I was making my favorite food, rice. So if I make rice, the right way to make rice, at least when I'm making it, is I get the same mug, the same cup of rice, and I fill my cup with rice. Now, if I want my recipe to work, I use the same cup, but I fill it up with water, 2 cups of water. So 1 cup of water needs 1 cup of rice needs 2 cups of water. And that's the recipe. In chemistry, we don't call it a recipe, we call it a ratio. But that's the same idea, recipe, ratio, my 1 cup of rice to 2 cups of water. But say I'm having friends around, say I've got guests coming, and I need 2 cups worth of rice. Well, now my 2 cups of water is not going to cut it. I'm going to need 4 cups. But that's okay because the recipe is still the same. For every 1 cup of rice, I need 2 cups of water, so 2 cups of rice needs 4 cups of water. And this is how a ratio works, is that no matter how much I scale it up or scale it down, I have to have the equivalent amount of the other ingredient, the rice and the water. If I check my cupboards and I am low on rice, and I only have about half a cup of rice, then the amount of water that I'm going to need is 1. So my same 1-to-2 ratio, 1 cup of rice to 2 cups of water, still works if I have half a cup of rice and a full cup of water. So my recipe maintains my ratio. And that's what's happening in a chemical equation as well. So I just change the amount that I add to make sure this works. It makes sense to think of, even if you don't draw it out, but at least have it in your head, a barrier between the reactants and the products. My reactants are on this side of the arrow, my products are on that side, and everything in has to equal everything going out. So my stock check, my inventory check, I've got carbons, I've got hydrogens, and I've got oxygens going in. So that means I must have carbons, hydrogens, and oxygens coming out. So my one carbon in equals my one carbon out. One and one. Okay, this is looking okay. And okay, right, here's our problem. I've got four hydrogens going in and only two coming out, two oxygens in and three coming out. So this is where I can start to change the recipe to make sure that this is going to work out. So my four hydrogens in, I've got to change it so it's four hydrogens coming out. Well, I can do that if I double the amount of water that's coming out. So twice as much water for the one methane, so the CH4 gives me now four hydrogens coming out if it's two waters. And that can change this one here. My hydrogen out is now four. So one carbon going in, one carbon coming out, four hydrogens going in, four hydrogens coming out. All right, this is working out. And now my oxygens, I've got two coming in and three coming out. But no, my three has changed as well because I had the two from the carbon dioxide and I've also got the two now from this water because I have twice as much of everything here. So 2 times 2 gave me the four hydrogens and the two oxygens as well. So 1, 2, 3, 4. So I have my four oxygens coming out. So now I can change the recipe on this side to accommodate the fact that there's four coming out. I need four going in. So what I could do is put a big 2 in front of this O2. So then 2 times 2 gives me four oxygens. And there we go. We have a balanced equation. One carbon in, one carbon out, four hydrogens in, four out, four oxygens in, four out. I balanced my equation. The concept of balanced equations was first thought up based on the works of Antoine Lavoisier, a wonderful French scientist who was part of what we call the chemical revolution of the 18th century. Antoine Lavoisier was a very exceptional scientist who came up with lots and lots of concepts, including the idea of the balanced equation, which was all about the conservation of mass and working out that you had to have the same elements out as the elements in. And he was one of the first people that realized that everything was made of elements. So he did an awful lot in the field of science. But one of the things that happened to Antoine Lavoisier was because he had a, a part-time job as a tax collector, the French Revolution happened around him while he was working on his science, and he had his head chopped off, which was not great for Antoine Lavoisier. The thing that was uh, a real shame, it's a shame when anyone has their head chopped off, but why it was a real shame for the French Revolution was Antoine Lavoisier was not a bourgeois, or at least not really. He definitely shouldn't have been tax collecting. But he was a rich nobleman for sure, so it would make sense that he'd be in line for the guillotine and have his head chopped off. But he wasn't bourgeois, as I say. He used his money to explore science. Unlike, I imagine, a lot of us who are studying science so that we can get a good job and have a career in mind, Anton Lavoisier, he didn't need the money. He was born with money. But he was interested in science. He used his money and his time to try and discover things. And he had his own labs and his own equipment that he paid for with his own money to try and put this together. And through his work, he discovered great things, not just for the great cause of France and the revolution, but for the world. All of us to this day still use information and discoveries that Anton Lavoisier made. So it was a real shame that he had his head chopped off. And the revolutionaries actually acknowledged this. They thought, oh, we probably shouldn't have done that. So what they did was they wrote a letter to Anton Lavoisier's wife to apologize for chopping off his head. Probably a little too late, too little too late in that case. Um, but they still did it. Still a part of history. To commemorate Anton Lavoisier and all the great things he did for France and the world, as I say, they built a statue of Lavoisier and they put it in one of the squares in Paris. So Lavoisier's own statue. Only the weird thing is about Antoine Lavoisier's statue was anyone who knew Lavoisier, they noticed that the statue looked nothing like him. There was no resemblance whatsoever. Eventually, the sculptor was brought to task on this point, and they admitted that they just had a mold of some other guy, and they thought, well, if we have the right nameplate on, no one's going to notice or care. And he was right. For the most part, nobody did notice or care, and that statue of Lavoisier was there in that square for a good number of years, until during the Second World War, uh, the statue was melted down and used for scrap in the war effort. So poor Antoine Lavoisier and his tragic life, and thereafter. I try to think of these things when I'm having hard times, or when I'm balancing chemical equations. Let's get a little bit more practice in balancing equations. So I've got a new reaction here. This is sulfuric acid reacting with the base sodium hydroxide to give a salt plus water. My salt is sodium sulfate and water H2O. So we've got all the formulas, and all the formulas are correct, but it doesn't balance yet. So let's do as we did before. Let's split this in half. Whether or not you write this out in the way that I'm going to do it, or even if you just kind of do a count in your head, it's good to kind of visualize this concept. Everything in has to equal everything coming out. And I do an inventory of everything that is going in. I've got hydrogens, I've got sulfurs, I've got oxygens, I've got sodiums, I've got hydrogens. So this is everything going in, and this is one of my tips. And maybe this is a little sneaky, maybe this is a little tricky. It doesn't always work, but it will work here. Is if you have any polyatomic ions, sulfates and nitrates and carbonates, I've got one here, an SO4. This is what we call a polyatomic ion. They're linked together, a sulfate, polyatomic, made of more than one atom, but is one ion. I've got a sulfate on this side, SO4, and a sulfate on this side. Now, this won't always work where it would stays SO4, SO4 on both sides. Sometimes that compound could break apart. It could lose one of its oxygens and become something else. And then I would need to split them into separate atoms. But while it's SO4 and SO4, I can be a little bit sneaky, and I could just put this as an SO4. So when I'm doing my inventory of everything in and out, I could just group this together because I know this balances. An SO4 and an SO4 going in and out still balances out. So hydrogens on this side, my sulfate on this side, oxygens, and sodium. Now, my next tip with balancing equations. I don't have a good reason why this works, but trust me, it does work. Is always leave oxygen to the end. I don't know why, there's just something tricky about oxygen. So I always leave it to the end. And quite a lot of the time is if I work everything else out first, the oxygens sometimes just work themselves out. It can happen. So just leave oxygen to the end is my tip. Okay, so I've got all these things going in and out. Now, nice and simple, I'm going to start with these sulfates because I know that works out. One in, one out. So sulfates are good. Now, the next kind of tip, which is not a great tip, which is I look for the atom that has the biggest number that's not oxygen, because I'm going to leave that to the end. So the biggest number next to it, well, I've got a hydrogen with a 2 or a sodium with a 2. I can pick either or, and I'm going to go for sodium. Why sodium and not the hydrogen? Well, because of this H2O, I don't want to be messing with oxygens just yet. So sodiums I'm going to go for first. I've got 2 sodiums coming out. So my sodiums, Na2 going out, so I need 2 going in. And that's easy enough. I can put a big 2 in front of it. There's only 1 in there at the moment. So 1 can easily become 2 if I just multiply everything here through by 2. So 2 sodiums in, 2 sodiums out. This is okay. 2 sulfates in, or 1 sulfate in, 1 sulfate out. And hydrogens. Let's do the hydrogens next. I've got 2 hydrogens in, plus the 2 over here, so that's 4. Let's write that down. So 4 going in, 2 here and 2 times this, so that's 2 and 2, 4. And then I've got my 2 hydrogens coming out on this side. So 2 on this side. I can make that a 4. All I need to do is multiply this through by 2. So I add a big 2 to say I've got 2 water molecules coming out. Then the 2 times 2 becomes 4. So now my hydrogens balance, my sulfates balance, my sodiums balance. Now those oxygens. All right, let's have a look at it. Now I don't need to worry about the oxygens over here because that sulfate I counted as one thing. So sulfate in and out is all good. So I've got 2 oxygens here. And then again, I don't need to worry about this oxygens here. It's part of that sulfate. And I have, 2 oxygens here. It worked itself out. Why this tip works, I don't know. Maybe there is a reason for it, but it's just something I've noticed. And it's my tip to you. Leave oxygen to the end. And look, everything else worked itself out. Okay, let's do one more. And make it a little bit trickier this time. Now on this one, I'm doing another neutralization reaction. I've got my sulfuric acid here again, but now I've gone for a different base, a lead hydroxide. And why this is a little bit trickier is because now I've got brackets as part of my formula. Now we're not afraid of brackets, we know what they mean, is it means that everything inside this bracket is multiplied by the little 4 that I've got here next to it. And then over on my product side, I've got the salt, which is my lead sulfate. Again, it's got brackets with a little 2 outside. But okay, we're okay with that. It just means everything inside is multiplied by 2 as part of its formula. And then an H2O. Okay, so my salt and water, this is another neutralization. So let's try and balance this out. I have hydrogen. Now I've got this sulfate here again, and my SO4, SO4. Just like I said for the last one, is if the polyatomic ion is the same in and out, let's just keep it the same. So I'm going to keep an SO4 on this side and on that side. I also have lead, and then I have another polyatomic ion, a hydroxyl, OH, but my OH does split up as part of this reaction, so I can't just count this as an OH in this case. I'm just going to use an O and an H. So those are all my elements going in, so they're going to be the same elements coming out. So in and out, what have we got? Well, just like last time, I'm going to go for the sulfate first. So my sulfate, I've got 1 of these going in, and coming out, I have 2. And that's what that bracket is telling me, that there is actually 2 sulfates coming out. But you know what? That's okay. We can balance our sulfates out by just putting a big 2 in front of the full thing here. It's going to change how many hydrogens we have, but we're okay with that. We'll balance them in due course. We've sorted the sulfates first. 2 in, 2 out. 2 and now 2. Right, sulfates 2 in and 2 out. The next thing, because I am keen to leave oxygen to the end, is... Oh, I've added hydrogen twice. I'm keen to leave oxygen to the end. That is my tip after all. So shall we go for leads? 1 lead in, 1 lead out. Okay, that seems fine. 1 in, 1 out. Remember that on this side here, the bracket means it's only everything within the bracket that's multiplied by 2. Same on this side as well. So I've not got 4, I've just got the 1 lead, 1 lead. All right, let's go for hydrogens then. So I've got my 4 hydrogens here. 2 times 2 gives me 4 on this side, plus the extra 4 on this side here. So that means in total I've got actually 8 going in. 2 times 2 is 4, plus the 4, 8. So I'm going to need 8 coming out. At the moment, I've only got 2, this H2. But okay, we can get it up to 8. It's a bigger number than the last couple of examples, but we know that if I've got 2 there, to get 2 to become 8, you just times it by 4. So I can put a big 4 there. Means I've got 4 waters coming out. 4 times 2 is the 8. Okay, all right. So our hydrogens balance, our sulfates balance, our leads balance. Now these pesky oxygens. How much do I have? Well, going in, don't need to worry about the sulfates oxygens because my sulfates SO4, SO4, that bit's covered. So I just need to worry about these oxygens. 4 going in, so 4. And then on this side, again, I don't worry about the sulfates, they're already covered. So 4 oxygens coming out. Amazing, it worked itself out. And there we go. That is our balanced equation. Now, the most important thing with balancing equations is it just takes an awful lot of practice. None of this stuff comes naturally or easily, or if it does, then you're a luckier person than me, because the way that I got good at them, if I even am good at them, is just through hard work, through lots and lots of times doing it. Just like playing a piano, you might have the concept down, different keys or different notes. I get it. Doesn't mean you're going to be able to play a concert recital until you practice an awful lot. Same goes with balancing equations. Lots and lots of practice is how you get good at it. Hopefully this video has helped. If you have any recommendations or requests for future Passmark chemistry videos and topics you'd like me to cover, then please let me know in the comments. And do us a solid and click that like button and that subscribe button. Thanks again. Bye.